let X be a Banach space and T be a compact operator and lambda be not equals to 0. And there exist unique natural numbers RQ such that 0 equals to this. So I know that I is the identity mapping, and since identity mapping is both surjective and inductive, therefore the kernel of I equals to 0. Now if I have an operator S and kernel of S is all such X, so if Sx is 0, implies that S of X is equals to 0. Therefore ker S is the subset of kernel of S square. Similarly, it is a subset of kernel of S cube and so on. Now this is in the case of ordinary operators, but now when this S is lambda I minus t, then at some point of time the equality sign appears, and then it remains so throughout. For general operators you might get equality somewhere, but it is not necessary that it would be equal from that point on. For example, here you might get an equality, but it's not necessary that the equality will continue here. But if the operator is of the form lambda I minus t, then once you get the equality it will always be equal. And another interesting property is that this would always be a proper subset, so that's why it is drawn first and then cancelled, so to emphasize the fact that it's a proper subset. So now the next thing that we're going to look is, I write my X as the image of I. Why can I write X as the image of I? Well, I is both surjective and injective, so image of I would be equal to X. So the image of S is the set of all SC such that C is in X, and image of S square is the set of all S of Sx such that X is in X. So if you are S of SC, then it implies that you are S of Z. So if you are S of this, so I write it as Z. So if you are S of Sx, then you are definitely S of Z, so this is a subset of this. And similarly you can do it in this way, in this progression. And now in usual normal case, it could be the case that you can achieve equality once and then again there is an equality. But in the case of operators where T is compact and lambda is non-zero and X is Banach space, then once you achieve this equality, so now you see that here once you achieve this equality, then everything up to q plus 2, q plus 3 and everything beyond is equal to that. And the case here is that when S is equals to lambda I minus t, in this special case, then you do not have equality at any point here. So all this is to emphasize that it is a proper subset, it is not equal in the slightest. So but in the normal case you might have that, suppose here it's equal, but here it's again subset. So this is the case here. And so now we see that let X be a Banach space, T is a compact operator, and the numbers R and Q in the previous theorem are equal. Which previous theorem? Well, so in this case, this R and Q, they are equal, in this case. And now we are saying that the whole of space X can be written as a direct sum of kernel of lambda I minus t to the power R, direct sum image of lambda I minus t to the power R. So every X in capital X can be written as y plus z, where this y belongs to this and z belongs to this, and the composition is unique. So this is the Riesz-Schauder theorem, and we're not again going into the proof because it's just linear algebra. If you want, you can have a look at it and post the doubts in the comments. Corollary says that let X be a Banach space, T is a compact operator, and lambda is not equal to 0. The Fredholm index of lambda I minus t is 0. So this is again a consequence of the theorem that we did above, and it's again a very simple linear algebra proof. We just need to keep in mind the statement of that as of now to prove some proofs later on. Now we have this proof before, that X is a Banach space, T compact, and the whole of x can be decomposed like this. And now we are saying that the Fredholm index of lambda I minus t is 0 if x is Banach, t is a compact operator, and lambda is not equal to 0. So now we do a remark. We do that the mapping lambda I minus t restricted to x1 from x1 to x1 is nilpotent with nilpotency in index r, and lambda I minus t x2 restricted, like lambda I minus t restricted to x2, like from x2 to x2 is an isomorphism, which means bijection. So now what is the definition of nilpotent? So nilpotent means an operator S from Z to Z with is nilpotent with index r. It means S to the power r is 0 and r is the smallest such number. That is, Z is equals to kernel of SR. Why do I say that? Because, well, SR puts, so when I do SR, then yeah, Z equals to the kernel of SR because SR puts everything in Z to 0, and Z is not equals to the kernel of S to the power t if t is less than r. Now I say that okay, lambda I minus t is nilpotent with nilpotent index r because we just see from the definition here, just look at here, if I apply lambda I minus t r times, then x1 is 0 because x1 is defined to be the kernel of lambda I minus t to the power r. So if I just apply this thing r minus 1 times to x1, then it would be 0 because x1 is indeed the kernel of this thing, you see. So we get this statement is pretty trivial. This is nilpotent with nilpotent index r. And the next thing we try to prove is that lambda I minus t from x2 to x2 is an isomorphism. How would we prove isomorphism? Well, let's prove that it is injective. So the way we would prove surjectivity is you have to see that, okay, surjective because now you have x is equals to x1. Now surjectivity follows from, if you look at this, so x is decomposed as x1 hot cross 1 x2, where x1 is the kernel of lambda I minus t to the power r and x2 is the image of lambda I minus t to the power r. Now if I apply lambda I minus t to x2, it means applying lambda I minus t to this one. So as simple as that, apply it to the space, the lambda I minus t goes inside, becomes to the power r plus 1, and from the previous lemma that we saw, that lambda image of lambda I minus t to the power r plus 1 is equals to image of lambda I minus t to the power r, which is exactly equals to x2, and hence space is surjective. And injectivity follows from this calculation that the kernel of lambda I minus t restricted to x2 is 0. So why is that true? Well, injective on only if kernel is 0. So the kernel is 0 because, well, the kernel of lambda I minus t restricted to x2. So the kernel of lambda I minus t restricted to x2 is all those z belonging to x2 such that this equation holds. Makes complete sense. Now I can write this z, now z belongs to x2, but x2 is the image of lambda I minus t to the power r. So this is lambda I minus t, lambda I minus t to the power r. X is my z for every value of x belonging to capital X, and then I just replace my z with lambda I minus t to the power r. So I get this, and then I can write this, so x belonging to x such that lambda I minus t to the power r minus 1 x is equals to 0, which means x belongs to the kernel of this. But we saw from a previous lemma the kernel of this is equals to the kernel of this. So hence we have lambda I minus t to the power r x this side, and x belongs to the kernel of this, so this is 0, and hence it's injective also, and thus we have lambda I minus t from x2 to x2 as an isomorphism. So now we have this corollary. It says that let x be a Banach space and t be a compact operator. So the spectrum of t outside of 0 is equal to the point spectrum. Moreover, every eigenvalue of t has finite geometric multiplicity. So let me explain this term, what it means. So by geometric multiplicity of an eigenvalue, I mean that let lambda be an eigenvalue of the t, and the geometric multiplicity of t is the dimension of the kernel of lambda I minus t, which is the number of linearly independent eigenvectors, which is also, so the kernel of lambda I minus t is the eigenspace, so the dimension is the number of linearly independent eigenvectors. Now I say that, so I write as that the spectrum outside of the spectrum outside of 0. So I have lambda I minus t such that lambda is explicitly not 0, where t is compact is Fredholm with index 0, which means by definition of Fredholm that the dimension of kernel of lambda I minus t is finite dimensional. So I can say thus, so I can say that when such is the case that the spectrum of t without 0 is point spectrum, and I say that the geometric multiplicity is finite. Now I know that the algebraic multiplicity is defined as, so the algebraic multiplicity of lambda is the dimension of the union of kernel of lambda I to the power I. So when I keep on doing this union, so I saw before, if you remember what we did before, so you saw all those kernels were contained within each other, and after an R the set became the same. So if I take the union of all such kernels, so let me call it say S1, S2, S3, S4, and if I take the union of all such S's, then after a certain point the S4 and S, so after S3 and S4 are same, and then S4 equals to S5. So if I take the union of such sets, then after a point, say after a certain R, the set remains the same. So I just need to do I is equal to, wait, so this is the case. So if I take the union of infinite, so if I take an infinite union, so I equals to 1 to infinity of kernel of lambda I minus t to the power I, but only till R are distinct. So I can just write that this is equal to kernel of lambda I minus t to the R, because after R this set is the same. So it's as simply as writing union of A and A. It's still union of A. So that is the logic behind that. Now going back to the point of algebraic multiplicity, I can say that the kernel of so this is the algebraic multiplicity of lambda. Now I know that if lambda is not equal to 0 and t is compact, and the algebraic multiplicity of lambda is the dimension of this, because it's only till up to R values. But I know that if I have lambda I minus t as Fredholm, then lambda I minus t to the power R is also Fredholm. So thus this is also finite dimensional, which means this will also give me a finite value. So this is also finite. So both the algebraic and the geometric multiplicity, when lambda not equal to 0, lambda, and for the spectrum of t, so let me put it this way, that every eigenvalue of t has finite geometric as well as algebraic multiplicity. So this is just the point that I want to make in this corollary. So the next thing that we're talking about is, let X be a norm space, T be a compact space, T be a operator belonging to the space of compact operators. Now it follows that the point spectrum of T is a countable set, The only possible limit point of sigma t is the origin. So now what I'm trying to say here is that if there exists a convergence sequence in sigma pt, then it converges to 0. That's all I'm trying to say. So you need to remember that if X is a norm space and T is a compact operator, then sigma pt is a countable set and the only limit point of sigma t is the origin. So here it's saying that the spectrum of T without 0 is the point spectrum. If it is the point spectrum, then lambda I minus T is not injective. If and only if kernel of lambda IT is not 0. So now what I'm saying in this statement is lambda pt is a countable set and the only possible limit point is the origin. And the next and the final point I'm saying that let X be a finite dimensional Banach space and T be a compact operator, it follows that 0 belongs to sigma T. Now how would I do that? Now I say that I prove by in converse. So I take let 0 belongs to rho T. Now 0 belongs to rho T is now is equivalent to if any lambda belongs to rho T, then lambda I minus T inverse belongs to Lx, which means 0 I minus T inverse belongs to Lx, which means T inverse belongs to Lx. Now T was compact, so bounded times compact is compact. I know that this is compact, which means that the identity is compact, and if the identity is compact if and only if X is finite dimensional. So the next thing that I would like to say is now I gave a complete characterization of the spectral value of my operator T. I have defined the spectrum of my T as follows. Okay, let's look at the proof as first. So it's compact, hence X is finite dimensional. So now let us summarize everything, and I can say finally that outside of the origin the spectrum of T consists of eigenvalues. So I just defined that sigma T outside of the origin is equals to sigma pt outside of the origin. So now this is the first thing. Now these eigenvalues are finite, algebraic and geometric multiplicity. What was the meaning of algebraic and geometric multiplicity? Geometric multiplicity meant the dimension of kernel of lambda I minus T. Now since T was compact, lambda was not equals to 0, so lambda I minus T is Fredholm. So kernel of lambda I minus T is finite dimensional, so dimension would be finite. And algebraic multiplicity was the union of I equal to 1 to infinity, the dimension of kernel, let me write kernel like this, of lambda I minus T to the power I, which now this reduced to lambda I from 1 rather than infinity, it reduced to infinity to R. And then this, now if I iterate after R, then R plus 1 equals to R, so it just became I from 1 to R, and the dimension also became finite because we know that lambda I minus T to the power R is also Fredholm. Now I say that okay, the only possible limit point is 0, where it says that okay, sigma T is a countable set, sigma T without 0 is a countable subset, and it says that only possible limit point of sigma T is the origin. Now spectrum outside the origin, that is sigma pt is countable, that was also a C, and 0 belongs to the spectrum if and only if X is infinite dimensional. So yeah, 0 belongs to spectrum. It follows that if X is finite dimensional, then 0 belongs to the spectrum.